Quick recap of capacitors. I know it's been a while. We said the current through the capacitor I equals C dVc dt. That means take the derivative of the voltage across the capacitor, multiply it by C. That will give you what the current through it. So if your voltage across the capacitor Vc is constant, that means you have a DC source. From calculus, what's the derivative of a constant? Zero. The current C times 0, which is 0 amps. So that's why we say the capacitor behaves as an open circuit to a DC. There's no current going through it. The only way to have no current going through something, if you have a hole in it, current's not going to jump. So the capacitor behaves as an open circuit. An open circuit to a DC source. And if we play with the math here, we covered that before, but we'll just revisit. It's been a while. If we multiply both sides of this equation, that differential equation, by dt, you will have I dt equals C dVc. Divide by C. Now integrate both sides from negative infinity to t. And you will see that the voltage across the capacitor at any given time, it's really the integral. We can take 1 over C outside, that's a constant, from negative infinity to t, I dt. And a lot of times you're not going to have access to negative infinity. You're not going to go back to negative infinity time. So this becomes 1 over C, the integral from t0, and that's the time when you walk into the lab and build the circuit, to t I sub dt, plus the voltage across the capacitor at t0. I don't want to use the word 0. I use t0. It could be 0. It could be any number here.
What do you mean by the time you walk into the lab?
Well, when you build the circuit, so sometimes you have a circuit, you walk into the lab. This is from minus infinity. You're not in the lab at minus infinity time, back thousands of years ago. So when you go to the lab and you build the circuit, and let's say there's your circuit, and there's some resistors here, and there's a source here, and you build that circuit, and it's running now for a while. So you're in the lab building. I said to you, you know what, why don't you go and disconnect this source? So you take this and disconnect it. It's not there now. Now what's going to happen, that source moved now, so we have to look, what was the voltage at that time when you removed it? That's the voltage here. Then it's going to start the discharge, because initially it's going to be charged. So that's what will happen. You'll see charge and discharge time. So you probably saw that in the lab when you're charging a capacitor. It goes like this, the voltage across the capacitor. It takes a while to charge, then it levels. And when you disconnect the power, when you shut the power off, and you watch the capacitor discharge, it goes like this. It doesn't just go to 0. It goes. Yep. And usually we're talking about milliseconds, microseconds. It's not going to be a long time. It depends on the values of R and C. So it does take a few minutes, and that's where the initial condition come in handy. What was the voltage of the capacitor when you disconnected it? That's where you were. Now it's going to discharge. If you want to hear a discharge, you actually, if you come into my office, I have speakers. And I'll be playing the radio there, and some people come to see me, and I'll shut the speakers, and you hear, and that's the capacitor really discharging there. That noise, I'm still picking that. So we went over that last time. So today we're going to add, that's the capacitor. We're going to talk about the inductor. Then maybe we'll put a sheet of paper side by side. Inductor, very similar to the capacitor. The difference, notice the capacitor here, we have I equals C dVc dt. The inductor, so you have an inductor like this, that's a coil, an inductor. This voltage is the voltage across the inductor. This is the current going through it, I sub L. The voltage across the inductor, VL, equals L times di dt. Just like I equals C dV dt, this is V equals L di dt. So that means if what? If my source, if this is constant, if the source I sub L is constant, what's the derivative of a constant? 0. Then the voltage will be L times 0, which is 0 volts. And to have a 0 volt, that means what? You must have a short circuit. If you short circuit something, the voltage is 0 there. If you open circuit, that doesn't guarantee the voltage is 0. 9 out of 10 is not. And the current source doesn't have to be a current source constant. It could be a voltage source that's constant. Because if you have a constant source, voltage source, is going to make the current what? Also constant. So to any DC source, just like the other one, we said inductors behave as a short circuit. Short, not open. Short circuit to DC source or sources. When you have DC sources in the circuit, that's all you got. That capacitor is going to look like, the inductor is going to look like a short circuit. The capacitor is going to look like an open circuit.
Now it looks like a short circuit because
There's no change in the current.
there's no change in the current.
So the voltage is going to be 0. The only way the voltage is 0 if you stick a wire there.
Isn't the current also 0 on the bottom?
Current for the inductor is 0, not for the voltage, for this one.
Oh, the change,
The derivative.
no change in current.
Change.
There is still a current going
Yep.
through it, whereas in the
Yep.
conductor, there's just no current.
Correct.
Got it.
This one has a voltage, but there's no change in the voltage. Remember, I could have a voltage source right here. But is that voltage changes here?
No, because there's
No.
there is
Yep.
no circuit.
So this one, I could have a current source here going through that of 5 amps. This will used to be my inductor here, right? So since that's a DC source, that's where my inductor here, that current is not changing, so it's going to react or behave as a short circuit. There's a current going through it, but there's no change in the current, which means the voltage is 0 there.
So inductors don't have any resistance?
Ideally, yep, we're talking about ideal.
I mean,
Yeah.
nothing's perfect. So
You'll see when we get to the wires in the lab, they have, especially when we get to the power, three-phase system and all that, there's power loss, and some of these wires might have 0.01 ohm in them, or 0.1 ohm in them in these wires, depends how long or how short the wire, what gauge and all that.
You know,
So
in-
ideally, we make that is 0 for now.
In circuits lab, even when you take like the actual resistance, not
Yep.
just the resistance that it gives you, when you put that through the circuit and you measure it all out, and then you take the experimental data and put it with the theoretical data, what it should be,
Yep.
it's not
Yeah, not much.
perfect.
And you're talking about the meter also, involving the meter with the
That derivative.
value in it there too.
There's a lot of sources
Yeah.
of error.
So now if you take this equation and you multiply by dt again, derive the equation, you end up with 1 over L, if you divide by L, V dt equals I sub L, or di, derivative here. I just multiply and divide by L. Integrate both sides. The current through the inductor at any given time, just like the other one, it's 1 over L, the integral from negative infinity to t of the voltage across the inductor dt. Again, you can rewrite that as 1 over L from t0 to t, VL plus the current at t0. Very similar. Let's take a few examples, go through them and see. We did the capacitor last time. Let's do some inductors. See if we can derive the expression for them. I'll slow down. Time, you all set? Okay. Now, here's my time, my chart here, or my input. Look at it. This is the current through the inductor, I sub L, in amps. And it looks like this. Starts from -1. It goes up to a value of 1. Here's 1. And stays 1 for 2 seconds. This is 2 here. Then drops down to 0 at 3. This is the time in second.
I think we did this once.
We did the capacitor.
Oh, we do this with
Now for inductors. Now, given the waveform, assume this is going through a 3 Henry inductor. So this current's going this direction. This is I sub L going through that inductor. We did the capacitor, but not the inductor, so that's why. Now find the voltage cross, or sketch it even. Let's find what that voltage is. Remember, it's the derivative. It's 1, the voltage, it's 1 over L. L di dt, not 1 over L. V equals L di dt. In a few minutes, I'll give you the voltage, give me the current. That's 1 over L. V equals L di dt, derivative. Now, if you look at that current, we can write the equation for it. It's really 0 all over except from -1 to 3. So from t between -1 to 0, that's a straight line going up, has a slope of what? 1. So it's mx plus b. 1t, what's the y-intercept here? 1. A straight line, the equation y equals mx plus b. M is the slope. The slope is +1 and has a y-intercept of 1. From 1 to 2, when t greater than 1 and less than 2, the value is constant. The value is always what? 1. And the last one, as t is greater than or equal to 2 but less than 3, it looks like it's coming down, has a slope of -1, -1t, plus, what is the y-intercept? If you extend that line, what's that y-intercept?
IT minus 1?
3, the y-intercept. Across the line of 3. Because the slope is -1, right? For every time you go 1 to the right, drops by 1. Or you go 1 to the left, goes up 1. Another 1, another 1. That'll be +3.
-1t or -it?
-1t. Slope. So can we find what the voltage? It's L times the derivative of that. Now L is what? 3 Henry times di dt. Let's look at that piece there. As t goes between -1 and 0, what's the derivative 1t plus 1? It's a math lesson now. What's the derivative 1t plus 1? 1 times 3? 3 volts. For t greater than or equal to 1 but less than 2, that's a 0 here. It looks stupid there. As t greater than or equal to 1 but less than 2, what's the derivative of any constant? 0 times 3, 0. For t greater than or equal to 2 but less than 3, what's the derivative of that? -1 times 3, which is what? -3. So if I graph that function, this is what my graph will look like. We know outside that's 0. This is the 1 here. This has a value of 1. It goes back to 0, then back to -1, then back to 0. And that's the voltage across the inductor at any given time in volts. And this is the time t in seconds. Yes. Oh, -3, I'm sorry. 3 and -3. The derivative is -1, but because the inductor is 3, it becomes a -3 and 3. Now, what happens in our circuit when we build them? We didn't discuss this, especially in digital logic. That's coming up next. When you want to go from 0 to 1, the device really doesn't jump from 0 to 1 quickly. There's a little bit of that little slack there. You know, it takes a few seconds to charge to go up. So let's look at this example. And let's say we have this signal. This is the current through the inductor. And I'll draw the current under it. Same scale. I'll try to keep the scale the same. Let's assume this how you said I want to go to 0 right there. You want it to go to 1. It takes a little bit of time to go to 1. It goes like this. There's the 1. Then it stays at 1. Let's say this value is 0.1 second. Negative. Now, when it hits 2 here, this is the 2, it doesn't jump straight down, so it goes a little bit slowly there. It goes like this. And let's say this value is 2.1 here. This is the 2 here. And it's the same inductor. The inductor has what? 3 Henry. This is the current going through it. This is the time in second. So what's going to happen to the voltage then? So what's going to happen? Let's look at the time to go from -0.1 to 0. That was a rise there. What was the slope? If this value is 1, by the way, what was my derivative? This is a slope of 10 now. This is 10t plus 1. So the equation here, it's 10t plus 1. T. What's the derivative of 10t plus 1? 10 times 3, which is what? Remember, V equals L di dt. It's going to be 3 times di dt. If the derivative is 10 here, what's 3 times 10? 30. So what you're going to see is actually a big spike in that voltage like this for that time of 30 volts. Then it goes back to 0. Now start to drop. Well, the equation for that, this one here, negative 10t plus some constant, the y-intercept. I don't really care what the y-intercept is, because the derivative of that is 0. So when I take the derivative of that, that's a negative 10. What's negative 10 times 3? Negative 30. So that's a negative 30 here. And that's a 30 up there. So you're going to see these big spikes in voltages there. And that might be actually trouble for us. If that spike is high enough and your circuit breaker is, let's say, can't hold that, you're going to blow up a fuse there. So these are impulses, basically. You have a spike in that voltage in short time, quick time. And as we get better and better at it, because one of the biggest thing is we're trying to do today is eliminate that little delay there, that time to go from 0 to 1. I don't want it to go slowly. I want it to go a lot faster. So eventually what I'm looking to accomplish is a device that will look like this. This should go up to where? To infinity. If that time becomes really small, 0. And down here to negative infinity and back to 0. That's what you're going to be seeing. So every week, every month, when you see your computer come in, we try to minimize that time, that little gap there. But that could be a problem for us. We have to make sure if you're building something, you're protecting for these cases. You don't want infinite voltage there. How many devices do we have in our radio or our iPhone that will hold infinite voltage there? I know it's a short time, but your device is kaput by that time. Okay, we derived the equation for the current. Let's take some examples on that. We said the current is 1 over L, the integral of t0 to t v dt plus I sub t0. So let's go through it and take some examples here. Again, the equation for the current, it's 1 over L, the integral from t0 to t, the voltage dt plus the current at t0. Let's see if we have an example. The voltage across a 2 Henry inductor is known to be 6 cosine. So here we go. There's an inductor. The value of that is 2 Henry. There's a voltage across that right here. And that voltage is known to be 6 cosine 5t. Determine the resulting current if current, what is find, so find the inductor through that if what? The current at negative pi over 2, they've given us that condition, is equal to 1 amp. Okay, let's figure what that is. Do some math here. Hopefully you all took calculus. You took Calc 2 at least. According to this equation, the current is going to be 1 over L is 1/2 from T0 to T. Take the voltage is 6 cosine 5t dt plus I sub L at T0. That's the equation for the current. Now, you know from calculus you can take the 6 in the front, that becomes a 3, right? How do you integrate the cosine of 5t? What's the integral of cosine 5t?
Negative 5 sine t, sine 5t.
I think it's sine 5t over 5.
Yep. It's 1/5
1/5
sine 5t, right? And there's the 3 sitting in the front. T0 to t. So you end up 3 over 5. Now let's plug in the limit. Sine of 5t minus 3 over 5 sine of what? 5t0 plus I sub L at t0. So that's the answer. The only problem is I don't know what these conditions are. If I know what these numbers are, I'm in good shape. There was a statement given to us here. I at negative pi over 2 equals 1 amp. That's T equals negative pi over 2. T. Let's plug it in. Plug into this equation. I at negative pi over 2 equals to 1, which is equal to what? 3 over 5 sine, this will be negative 5 pi over 2 minus 3 over 5 sine 5t0 plus I sub L at t0. Now, unit circle. Let's see if you remember unit circle. Negative 5 pi over 2, right? This is what, 2.5? Negative 2.5 pi. This is negative 1 pi, negative 2 pi, negative 2.5, right there. What's the sign of that angle? Negative 1. If you have the unit circle, the sign down there is minus 1. So that would be 1 equals, this is a minus 1. Minus 1 times 3 over 5, negative 3 over 5, minus 3 over 5 sine 5t0 plus I sub L at t0. Bring this number to this side. That becomes plus 3 over 5. 3 over 5 plus 1, that's 8 over 5. Now, can I give you the equation for the current? Absolutely. From here, what's the equation for the current? It says 3 over 5 sine 5t. Let me take a closer look at this. What is that equal to? Isn't that this piece right here? Which is what? 8 over 5. So here's the current now at any given time. You tell me the time, I'll tell you what the current is. That's the equation for it. .6, if you're going to use decimal value, it's 0.6 sine 5t plus 1.6. My phone is reminding me we have test.
videos has like a few hundred views.
A few hundred?
Yeah, the Queen McCluskey.
Really?
Yeah, so I'm like, wow. I guess,
There's some comments.
yeah.
People like it.
They do?
Yeah. It's like, oh wow, thanks. It's so clear. Like, get that one.
Wow.
Hey, man.
Oh, I never look at them.
You're a YouTube star.
Well, you know what happened? Actually, the young guy just took a job at Winnick. I mean, at HCC. What's his name? He's a tutor for us.
So Armando.
Armando, thank you. I had him for a few years. I forgot his name now. Armando asked me if his kids at Holyoke struggling. Is it okay if they use my videos? I said, go ahead.
Oh, maybe that's what it is.
So maybe some of his students are using it. I don't know.
I found them really helpful.
I'm glad. Because honestly, no extra work for me. You can see. The only extra work, I just gotta go and put them. I gotta go to my office and wait half an hour to go to YouTube. You know.
Is it like set by default on private? Like some of the videos.
Yeah, one of them
are
was on private, the very last
like,
one.
Oh, that's by mistake. I have to fix it. Do you know which one?
The
The PLA.
latest one you did, the PLA one.
PLA said on private. Yeah, I gotta fix it because one of the option is private, or so I gotta find it.
Yeah.
PLA, you said. So you couldn't see it. The PLA, right?
I'll double check real quick, but I believe that's the PLA. Like, there's two PLA ones, I think. It's the second one, I believe.
The PAL is supposed to, oh, it's a PAL, sorry. PAL.
PAL is private. Okay, I'll double check them. I didn't mean it that way, no. Sometimes I'm just clicking. I'm talking to students. I'm clicking, and it goes to different directions. Okay. What about the power? I started doing that last year when I was teaching physics online, algebra college physics, and I made 30 hours of videos to put them on the stuff for the kids to see. Kids in physics not easy to.
Yeah, PAL.
PAL.
PLA is fine. I think I remember watching that one last
PAL. So I'll do it. Yeah. I'll fix it. Huh?
You're still recording.
Oh yeah. Oh, well, it makes it more fun that way. People get to listen to our conversation. You know.
I just didn't know if you wanted to.
No, I'm just going to finish the topic with this one. Now it's the energy or power. Well, we know power. We can derive the equation. Power for inductor, again, for anything, is V times I. You can do V is what? L di dt times really I. So you end up with L I di dt. That's what power is. If you multiply both sides by dt to cancel that dt here, so L I di dt equals p dt. Wait a minute, let's integrate both sides. What's the integral of power? Energy. So it's equal to L. You can take L out. What's the integral? Oh, the dt is gone, right? Di here. The dt is gone because I already. The integral of I di. What's the integral of I di? Isn't that I squared over 2? So that's the equation that you see. The energy stored in inductor as a function of time, it's 1/2 Li squared. 1/2 Li squared. Just like the capacitor, 1/2 CV squared, this is 1/2 Li squared. So if I take the capacitor and the inductor and put them side by side in a nice clean way, I'll try to use a normal pen. Just summarize them side by side. Capacitors and inductors here. For inductor, V equals L di dt. Again, inductor will look like this. This is the voltage, and this is the current going through it. The capacitor will look like this. This is the voltage, and this is the current through it. The value of this farad, C farad, this is L Henry.
They go by Henry's.
Yeah, inductors by Henry's. I don't want you to think CF, but C farad, I just go C in farad, and I go L for Henry, yeah. The unit's Henry's for inductors. So V equals L di dt. The other one is what? I equals C dV dt. Now the other thing, to DC sources, the capacitor behaves as what? Open circuit, which means the current will be 0. To DC here, the inductor behaves as what? Short circuit, which means the voltage is 0. We also looked at the equation for V here. We said for a capacitor, V is 1 over C, the integral of I dt, from negative infinity to t, which you can break it down to two parts. You can say it's 1 over C, the integral from t0 to t I sub dt, plus what? The voltage at where? At t0. This one says the current I, the current across the inductor I sub L, is 1 over L, the integral of V dt, from negative infinity to t. And I can break it down to 1 over L from t0 to t, V dt, plus the current at t0. This is the current through the inductor at any given time. This is the voltage across the capacitor at any given time. And the third equation, when you put them side by side, the energy stored in a capacitor, 1/2 CV squared. The energy stored in an inductor, it's 1/2 Li squared. You can see the equations are very similar. When you look at them side by side, they're very similar. I becomes V, and V becomes I. Just flip-flop them, basically. Again, both of these are known as energy storage element. Again, they don't absorb the power or the energy. They don't use it. They just hold it, and then they release it. Hold it and release it. The book tries to summarize what we said here, and I'll show you. Important, it says here, talking about inductors, ideal inductors. V equals L di dt. There is no voltage across the inductor if the current through it has no change. It's not changing with time. If the current is not changing, the derivative is 0, the voltage is 0. Therefore, the inductor is a short circuit to DC. A finite amount of energy can be stored in the inductor, even if the voltage across the inductor is 0. such as when the current is constant. When there's current going through that constant value, there's energy stored there. It is impossible, that really becomes important when we get to the next chapter. It is impossible to change the current through the inductor in a finite amount of zero time. Notice the reason we said it's impossible, going back to this equation, V equals L di dt. We're saying you can't change the current in zero time. Because if this number is zero, what will happen to that number? What will happen to the result here? It becomes what? Infinite. The same thing right there. It is impossible to change the voltage here in zero time. So when we get to later in the course, you're going to see me write the voltage across the capacitor, because it doesn't change in zero time, at T0 minus is the same as the voltage across the capacitor at T0 plus. It doesn't change in zero time. It takes a few seconds, milliseconds, microseconds to change. The same thing here. The current through the inductor at 0 minus is the same as the current through the inductor at 0 plus. Otherwise, if you let it change in zero time, you have an infinite voltage and infinite current. We have a problem. Going back to these pictures I drew early. This one. If we allow it to change in zero time, you will have an infinite value, negative infinity on this end, which is not something we're looking forward to. So that's another one actually we use, that the voltage across the capacitor is 0 minus, the same as 0 plus. The current through the inductor is 0 minus, the same as 0 plus. It does not change in zero time. In the last statement, the inductor never dissipates energy, but only stores it. Although this is true for mathematical model, it's not true for physical model, because we're making the assumption this ideal, there's no resistors in them. So on math, on paper, we said they just store the energy and release them. In real life, there are resistance to them, and we're going to lose some of that energy. Now, what about if we put inductors and capacitors in a problem? If you see more than one inductor, what do you do?